Okay, welcome team. Um, so let's start the session for today with a recap of what we have discussed yesterday. Uh, so we have done the JSON processing, how we process the JSON. And okay, before that, let me start my cluster. Give me 1 second. So, compute. So while it is getting started, so what did we talk about yesterday? We talked about JSON processing. I think that part is clear with everybody. So has anybody tried with the custom data set that we discussed about for the JSON with the event hubs? No? Okay, that's fine. So apart from that, we talked about the DAG. Spark, how does Spark process based on the DAG it generates? Directional acyclic graph. So we talked about any processing, any notebook you write and you run, it does not immediately start executing line by line. It will at a later point of time. So first it will scan through the entire notebook or the whatever thing that you have executed. And then it will generate a graph, basically how it is going to execute that. So to do that, it uses two categories called transformations and actions that we are doing. Now, what is a transformation and what is an action? So transformations are basically what we do, like read, select, filter, aggregate, and few other things like what you say, with column, add column, drop column. So all of these, join. So all of these are basically your transformations. You're transforming the data. Action, on the other hand, is you are actually looking or doing something with the data, basically display, okay, or show or collect is you are viewing the data, or you're moving the data from the workers on to the driver, which is called collect, will show what is the driver and what is it, or writing to the database, right? So these are basically the actions. Now, Spark 1 works on a concept called lazy evaluation, which means it will not start execution until you have an action in your notebook anywhere. So if you just write a bunch of transformations and run it, nothing happens. Okay, even if you write 100, 200 transformations, it will just read it, scan it, read it, keep it DAG, and then leave it. That's it. Unless there is an action, it does not start execution. So that's called lazy evaluation. That's how Spark works. So we can try see that, until there is an action. We have seen, like, whenever we run some cells, it says done less than 1 millisecond, or 1 second, less than 1 second, kind of a thing. And you don't see the progress bar, or you don't see the job running at all. It just kicks off some jobs just to scan if there is a file, to get the metadata about the file. Say if you're a CSV, you're reading a CSV file, to get the metadata of, like, what is the number of columns and what are the data types and all, just to give you when you click those jobs, the output it gives you the structure of the data frame or metadata, but it does not execute or process anything. Okay, so that is the lazy evaluation. Are we clear till here, Hitesh?
Yes, sir.
Okay. So the next step now, what does a DAG actually contain? Now you say like, okay, it's a lazy evaluation. We have a DAG and it runs when there is an action. So what does a DAG actually contain? So DAG has something called stages and tasks. Okay. So what does a stage and task mean? So stage is like you're splitting the job into multiple components, smaller parts, basically, dividing the job into smaller parts. Okay. Now, each stage, okay, how is it? What is the boundary of the stage? When does it create a new stage? How does it decide that, this stage has to end here and the next stage has to start? So let me share my screen here and then we'll talk about it. So we go here. Go here. Yeah. So if you see here, we looked at it yesterday. When at the beginning of the class, it was very complicated. And I think by the end of the class, we all understand how this is done and what it is, how simple it is. So basically, whenever there is a shuffle of data, okay, there you create a new stage. Okay. So basically, when there is a shuffle of data, what does shuffle of data mean? Again, it connects back to the concept of distributed computing. So that we will discuss today in detail. Distributed computing in the sense, if you have a data frame, we have to visualize the data frame is not sitting on one machine. Though it looks like one table, one object, internally it is residing or located in multiple machines, nodes. So each machine or each node has some part of the data. If it has million rows and I have 10 machines, some machine can have 100,000, some machine can have 200,000, some machine can have 150,000. So that million rows is distributed on all 10 machines. So whatever processing you do on those million rows will be done by all the machines on the part of the data they have. Okay. So let's say for the million rows, you are calculating, like we talked about, square root. Okay. And the new data frame for each of the there's a million numbers or whatever, and you are calculating the square root. So calculating square root is the let's say task or process. Let's not use the task again, you get confused. Is the process or is the job function that you want to do. So that function is not running on one data set at one location on one machine. So since you have 10 machines, for example, so the same function is sent to all the 10 machines. Okay, this is the concept of map reduce, right? When it is coming from the last, when we started the big data and Hadoop and map reduce from those days. So that's the concept. Like the data is not coming onto the code base. Rather, the code base is going to the data and executing on the parts of the data, whatever machine it has. So all the 10 machines has parts of data. So you're sending the function there and that function runs on that data, which is there on each machine. So once all of the machines are done, then you get one data frame from all the machines whenever you want to do anything with the entire data frame. Until then, it still resides on each worker. Okay, that's what the concept is. So that's a distributed computing. Now, when you are processing that, sometimes you may want to, or it is required to haul the data over, move the data between the machines. Okay. Why do I want to do it? Say some machine out of a million rows, say one machine has 500,000 rows and other 9 machines are having 100K, 50K, 200K kind of a thing. So that is uneven distribution of data. So when you are doing calculation of square root, all 9 machines finish faster because they have less data. The 10th machine may take longer because it has more data and more than 500,000 records. So, but until all the machines complete, our job is not complete. So all the other machines complete their task and then sitting idle while the 10th machine is still churning or running the job, right, for say hours to complete 500,000. But the overall job is only completed when all, even the 10th machine is done. So the overall time taken is more, or it might hang, or it might go out of memory, right? Errors. So in that cases, what we do, we want to do somehow redistribute the data to all the machines. So something called repartition. Okay. So 10 machines have 10 partitions, but one is a bigger one, smaller one. So we want to do a repartition of data into, so that all machines have more or less equal, similar kind of data, if not exact number, but more or less similar volume of data to process. In that case, what has to be done, you have to move that 500,000 rows on one machine to other machines, some of the data. So it's called shuffling. Data is shuffled across, moved across. So whenever you do a shuffle, there is a network IO, there is a CPU, all of these resources are required, right? So that is the one of the critical operation that you have to be aware of when you're writing the code. How often are you shuffling the data? Is it required or can we avoid, right? Those kind of things when you write the code. Now, why we are talking about shuffle is whenever there is a shuffle, this Spark engine creates a new stage. Or in general, so what here it is showing is, it is showing two data sets with some sort and merge kind of a thing operation. So this is a data set 1 in stage 0. This is another data set stage 1. It has read both the files. Then from here, there is some shuffling exchange. So it has done repartition of the first file. Then it has done repartition of second file maybe. So there are different stages that are created. Then we have taken both the files and then did a join here. So there's another stage. So when the shuffling happened to join those two data sets, and finally there is repartition of the processed or merged joined data frame that was joined using those two data sets. As long as there is no shuffle, whatever transformations you do on the data set, okay, like if you want to do a filter, select, or with column, drop column, everything, it will be done within the same stage if there is no data shuffle kind of a thing, right? So that is the whole purpose of a DAG. Now, when you do a DAG, we have seen yesterday that you have stages, and then in each stage you will have tasks. So task is basically your lowest level of the working component. When you say the example of doing a square root, the task is actually doing the square root. Now, how many tasks that is it create depends on number of cores in the cluster. If you have 100 core cluster, the parallelism you talk about is at any given point of time, you can run 100 tasks in parallel. So each core can take up one task. Of course, there will be some cores that will be reserved for memory overhead and OS operation and all of that. But in general, if you have 100 cores, almost 90 to 95 kind of tasks that you can have generate in parallel, run in parallel. So what does that mean? If you have 10 machines and each machine is 10 cores, and if you have 200 partitions, right? And if you have a 100 core machine, so 100 tasks will be run in parallel, which means that 100 partitions will be done in round one. Once the task is completed, the core is, then it will create new task to run on the other partition. Okay. So parallelism is defined basically between partitions and cores. So as long as, so these are in, as long as these two are considered, you can tune these two to have a maximum parallelism, right? So for example, if I have like 100 core machine, okay, and I have data in 2 partitions, what does it do? I have data in 2 partitions. I have 100 cores and I run the job on all 100 cores. What does it do? How many tasks are created? How many jobs, how many cores are running parallel?
100 plus
100. Okay. Any other answers?
200.
200. Any other answers? Okay. So there are only 2 jobs or 2 tasks that can run. Basically, because you only have 2 partition. 2 cores cannot process on the same partition, right? Because if I am doing something on a job, something else cannot come and do it on the same thing, right? So 2 tasks will take up those 2 partitions to run, and all the other 98 tasks will just be idle because they don't have a partition to work on. So in that case, what you do is you do repartition because I have a 100 core machine. Okay. And I can run 100 tasks in parallel. But to run that, I need to have some data to work on. So what you do, those 2 partition, you will repartition to 100. Then it creates 100 partitions, and your 100 cores can run on 100 partitions in parallel, 100 tasks. Or he can do 200 partitions. That is fine. Partitions can be more than the cores. So in the first part, all 100 tasks will take up 100 partitions, process it. When it is done, then they take the next partition. As and when task 1 completes, it will take next partition. So it's basically you visualize just like physical work. You do, some people are there. Let's say you have to in a workshop, you are trying to get some boxes and put it in the shelves, right? And if you have 100 people and there are 200 boxes to be packed and put it, each person can work on one box to pack, right? So 100 people will take 100 boxes, start working on it. Whoever completes his task, he will pick up the second box, right? So like that, as and when the task they complete with the first partition, they will take up the next partition. That's how the parallelism works. Now, to get maximum parallelism is what we are trying to do. That's why we do the repartition, so that all the tasks will have some job, some kind of data to work on, so that they don't sit idle, right? You don't want 2 people working on and if there are only 2 boxes, I won't get 100 people, right? And then 2 people are working on the boxes and 98 people are sitting idle. So basically, we create more number of data partitions. To do that reshuffling, again, there is again some kind of IO and some kind of CPU that is involved when you want to repartition that data. So that is a trade-off you have to see. Do I do the shuffling and then use all 100 cores to do it faster? Or, hey, my 2 guys are good enough to do the boxes on 2 big boxes, partitions. I don't need 98. I don't want to shuffle them across the network. That is taking up more IO and CPU and all of that. So it's a trade-off, but most of the times you do repartition. But in general, also Spark will automatically create more or less equal partitions. So basically, so that's the concept. Now, why we are talking about that is, so that's where we do this data shuffling, repartition, or when I want to join 2 data sets. So when I want to join, it is easier if the keys of both the data sets that I'm joining are on the same machine. Otherwise, one record from this machine has to join with a record on the other machine to pull the data together, right? So if we do the shuffling, whenever there is a join, it gets shuffled based on the keys that you are joining first. And when the data is co-located on the same machine, it joins with the 2 data sets within that machine. whatever data that is available. So that is the kind of DAG that we have seen yesterday when we did the when we ran the job, right? We can do so employee department that we talked about yesterday, and I can take this just to a run all. So we have seen what we are doing. We are reading the data from employee salary data set. Then I'm reading data from department, and then I'm doing repartitioning of these two data sets. Then I'm joining these two data sets and doing a display. Okay, so this is all I have done. So whenever there is a display, this is where so there is no display anywhere. So there is no job that is done. So here it has all the jobs, and this is the tag. Okay, so if you see, we have the same kind of DAG here, which does reading the first file, reading the second file, then kind of repartitioning these files, then join these two files, and then group by action here. Shuffle, read, all stage code. So each stage has, wherever there is a data shuffle, there is a new stage that is created, apart from getting each data set differently. Okay, so that is kind of a recap on the DAG. We talked about, how it kind of done this. So we said we'll have tasks, completed stages, okay. So we also discussed about each of these jobs, stages, and sequels that it has run, right? All of this. So what happens when you run the each of these sequels? Exchange, scan, hash aggregate, broadcast, hash join, what join it has used when you are doing a join, all of this. Shuffle reads, adaptive spark plan, all of, no? So physical plan you can see, initial plan you can see for each of the SQL that you are running. Okay, and then you can also look at what is the join that it is using, join strategies. This is all just like to understand at a high level. So I'm not expecting you to go through each line by line and try to understand what it is doing. Just to know at a high level, what is DAG, how it is executed, when is each stage created, how parallelism works, right? And then when it is a join, how does it do where you can see the physical plan and the initial plan, adaptive spark plan, what kind of join strategies that it is using in the joins, and how it creates this DAG kind of. So whole stage code gen is basically where it generates the actual code to execute. Okay. Cool, guys. Right. So let's move on. I want to talk about mentioned, right? So some of the concepts here. So what I was talking about, right? So data shuffle and to read. So how does the map reduce or the distribution of data works, right? So if I have an input file like this, I want to do a word count of all of these words. So what it does is it split into smaller data sets or partitions. And these partitions are distributed across your machines, cluster machines. Now, let's say each deer is one, bear is one, river is one, car one, river. So just giving a uh, number one count to each of these, right? Then comes shuffling, because if I want to count bear, I know bear is here, but I don't know where the other bear is and what is the count. How do I get the total count from here? I don't know what is there on the other machine. So what I will do, I will take, okay, all bears together. So bear one, I move here, and another bear from this machine will move here. Then I get all cars to one place here. Then I get deers to one place, and I get river to one place. So you just don't think that these are different machines. These are just partitions. Okay. Now, there might be, we thought about only three partitions. There might be only three machines. So two of the partitions can be on the same machine, and each other machines can have one partition each. So it's not like one machine, one partition, one on one. So don't think about that. Each machine can have multiple partitions, but one partition should be fit into one machine. A partition cannot be spread into multiple machines. Okay. Did you guys get all that concept?
Yes, sir.
Okay. A data frame can be split into partitions. So a data frame will be split into partitions. The entire data frame will exist in multiple machines, parts of data frame. Okay, if a data frame is split into 5 partitions, and if you have 3 machines, it is possible. Well, first machine can have 1 partition, second machine can have 2 partitions, and third machine can have 2 partitions, total 5. Or first machine 1 partition, second machine 3 partitions, and last machine 1 partition. That is also fine, whatever it is, like, total 5 partitions. It is okay. But partition 1, half of the partition on machine 1 and half of the partition machine 2 will not happen. So the entire partition you do has to fit within one machine. So for example, if I have a file of 100 GB, okay, and then I'm just only splitting it into 4 partitions, and then I have a 25 20, I have 4 machines, each 25 GB, and then I took 4 partitions. But let's say one partition is 30 GB and the other partitions are 20 GB. So 3 partitions will fit, but the one machine which has only 25 GB cannot hold all 30 GB of data when you do that partition. So that is when it will spill over or you get out of memory issues. So one partition should be fit into one machine completely. So that's the reason. Okay, coming back here, I have 4 3 partitions here are now shuffled into 4 partitions when I do the shuffling. After this, now I can do a count of this partition here itself. All the data is here. So bear 1 plus 1, 2, car 3, deer 2, river 2, and then final result is sent to the driver. So this is how distributed computing happens. You are taking all of this, distributing it to multiple machines. Each machine will do its part and then send it back its result. And then we consolidate the entire result here. So this is the MapReduce algorithm. Basically, when Hadoop started with and big data and Hadoop started, it started with this concept of MapReduce. But we are actually manually writing those algorithms for mapper and reducer. We used to write those functions in Java. What is your map function? What is your reduce function? And all of that. That was long back, legacy. Right now, everything is managed. You don't have to write anything at all, map or reduce or whatever. Of course, there is a transformation called map. There is a transformation called reduce in Spark that you can use. Okay, map says, say if I'm transforming the data x into square root of x, the other example. So I can just write data frame dot map, take x, and then say do square root of x. That's it. So it will take that function, it will send to all the partitions, all the machines, and then it will distribute and run on all machines and get the result back onto the data frame. So that's the map function. Reduce also you can write if you want to fold, unfold. There are a lot of functions, but let's not dig deeper there for now. Getting back, same concept here. When I get into a, let's say, yeah, sorry, a question?
In the previous slide,
Mhm.
So when we are in the mapping
Mhm.
section, we are assigned, so 111, right? That indicates the number of partitions, right?
No. No partitions. This is just to sum, count. So this is just assigning a number 1 that, hey, deer, I have 1 here. 1 instance of this word, deer.
Okay.
1 instance of word car, 1 instance of word car. So that when I want to count all cars, I will do 1 plus 1 here. So it will become car 2. Okay. So here, if I move all cars, when I want to do the sum, what I will do? Car 1 plus 1 plus 1, 3. That's it. To facilitate this sum, I'm just assigning a number 1 to each. That's it. It's not partitions.
Okay, it's just the uniqueness. So
Yeah,
one
yeah.
here, one there, one river.
Cut. That's it.
Then, okay, yeah, shuffling. Okay. Then the count is basically total number is when we are reducing.
Instances, yes.
Okay.
Okay. So this is just one example. Now, as I said, right, it can be any function that we are trying to do. Okay. So if I come here, all I want to do is sum of all the dollars for worker or salaries or whatever it is, payments to be made. Now I have 6 employees. I have to pay the total amount. Now I say each of these employees are on different worker machines, the data. Employee 1, 2 are on the machine on a worker 2. 4 and 5 are on machine, worker 1. 3 and 6 are on a machine, worker 3. This sum function, when I say sum, just like I did here sum, so that sum function is sent to all the workers. Hey, this is what you have to do on the data you are holding. Now forget about how many partitions are there in this. So that is the next level. So we are going at one level up at the worker level. So all the master sends to worker is that, hey, you have to do this job on whatever data you are holding, sum. So the worker 1 will take and run the sum on all the data that it has. So internally, this worker is what it may have executors. It will create tasks on each partition. So this may have 5 partitions or 10 partitions, run the data on all partitions, and then create sum. Same thing for worker 2, same thing for worker. So then when they are done, they will say, go back, master, I am done with the job that you have done, that you have given me on the data I hold. So my sum, okay, is 450. You take it. Worker 2 will give, hey, the data I hold, the sum is 650. The data I hold, the sum is 300. Now the master will take and sum all of this. So that is 1400. So this is how the distributed computing works. Instead of adding all of this here, it goes like this and then comes here. Now you might ask, why all of this thing? It is easier, no, just to add here. That is much easier than sending this here, getting back here, and then again adding it here. This is just an example. It looks simpler, but think about the same thing goes for a million rows. And you won't always do a sum, right? There are a lot of complex processing that you do. Joining two data sets based on keys, okay? Or calculating the Euclidean distance or whatever, machine learning, whatever tasks you do. There is huge amount of work to be done. Okay, so everything cannot be done in the master. First of all, if I have a 100 GB file, I cannot even fit on one master. I have to have a huge server to hold 100 GB in memory and then do all the processing. That's why we do the distributed processing. This is just an example to understand how the job is split and function. The processing is split between workers to distribute the work, and they do their part and give it back to get the sum. Is it clear? Any questions?
And the same is true whether it's a single node or multi-node. It's it's basically number of threads available within one node, and the same concept applies for multiple nodes also.
No. So basically, these are your nodes: worker 1, worker 2, worker 3. If you have only one node, basically your master is your one node. So all the data is still on your master only. So everything you are doing in the master only, single node. You are not doing a distributed, or basically you are splitting the partitions within here. Your node itself will have 3 or 4 partitions, but you don't have any other workers to do work for you if it is a single node cluster.
Okay,
Both
so it's not
both your driver and worker are all on the same machine. If you have one node, means you have only one machine. Then where are your workers?
So if it's not worker, you're not talking about
Again,
threads.
the
About
Raju, can you please? Sorry, Anush, I'm not able to hear you. Can you be a little?
So basically, when we're saying workers here, it is not threads. It is basically worker nodes. I mean,
Yes.
on each node. Got it. Okay.
Yes. Yeah. So if you go here, then you will understand the next slide. So this is a typical Spark cluster. So what it does is you have a driver program and a cluster manager. So these are your worker nodes. So this is machine 1, this is machine 2. Okay, node 1, node 2. In this, as I said, there is an executor. The executor will create tasks, and then it will create cache within that if I need a cache. This executor will create tasks. So here it is creating 2 tasks, which means it is using 2 cores to create 2 tasks to work on that. Here, 2 cores. So basically, if I have 4 partitions, 2 partitions can be worked on parallel here, 2 partitions can be worked on parallel here. So total 4 partitions can be worked in parallel here. The driver, the Spark context, whatever when you do spark.read, right? So that is the Spark context. Initially, in the initial days, when we write programs, we used to actually write code to create Spark context. Just like boilerplate code. The first line used to be like sc is equal to spark.create Spark context. And then we used to give some configuration to create that object. Then we used to create a SQL context object to run any of the SQLs. Then using those objects, we used to write all the other programs. Now all that is even now, I think if you write a standalone Spark program out of the Databricks, it is now when you import the library, that object is automatically created and given it to you. But initially we used to create that object separately in the program on the first line, and then use that object to run all the program. Right now, whatever you do here, Spark dot, what you are doing here. The Spark, this object is your Spark context, right? So this is the Spark context that is created on the driver program. It's called the driver. It's always on the master. node, the driver. So this will Spark context will give the jobs to the executors, and executors will execute, the workers will execute using the executor and give it back. The cluster will manage the worker nodes. It's basically whether the node is working fine or node is up or heartbeat, getting the heartbeat and seeing everything is okay with the worker, or if it has gone down or having issues. So that is done by the cluster manager program. And this is all, you don't need to create anything at all. When you create a cluster, everything is taken care of. Everything is created for you and taken care of. You don't need to do anything. All this. If you create a 3-machine cluster, 4-machine cluster, everything is created and then taken care of. Initially, we also used to define what is the executor memory, what is the worker memory, what is the driver memory. Now, all of that is not needed. It is automatically taken care of. There are options when you create the cluster, right? Yesterday, we have seen in the, when Anush was showing the machine in the Azure Databricks, it says what is the machine, how many cores it has, what is the memory. So based on that, it will create everything and manage all of this. Clear how Spark processes any of the data frame or the files data that you are reading? Any questions on this? Vamshi, Hitesh, Raju, Naina? So
Yes,
these
sir.
are like, these are like more like concepts that you have to
So
remember.
this driver program is the program that we write in the notebooks, right?
Yeah.
So that's the driver program is nothing but the code that we write. It
Yes.
can be Notepad or it can be
And it's Spark,
notebooks, or it can be a Java or a Python
yes.
program, right? So then what we say, okay, first talk to cluster manager, and
Yeah.
then what you, as like you mentioned, we write a code that code is given, okay, talks to the cluster manager, and then it tells, okay, here is the
The cluster
sequence of
manager.
steps.
The cluster
Right.
manager will tell you how many workers are there, how many executors are there you can use to get your job done, how many partitions are there and all of that. Then the Spark context will send what each worker has to do on that data, that job. So whatever transformations you write, so those transformations are sent from Spark.
Okay. So you said previously, you said the code is provided to the worker nodes, right?
Yeah.
So what it means is this Java program, the program that we are writing, and we are calling Spark context.
Mhm.
So Spark context will take the DAG.
Mhm.
Will it form the DAG, and then will it form the DAG, or a cluster manager forms the DAG? Because
No, the driver,
our is just a
cluster
code.
manager does not do anything except for
Any
manage
DAG.
the workers and master, communication between the worker and the driver, and between the worker nodes. If I have to do a data shuffle, I have to move from this worker to this worker. So those kind of things, the cluster manager will take care of communication between your nodes and the driver.
Oh.
Actual job or the transformation, what you have to do, that code Spark context will take care of. Like, for example, if I go here, I'm saying df data frame dot repartition. So I want to repartition this data frame to four partitions. Okay. So if I want to do that, the Spark context will go and tell, the workers that, hey, whatever the employee data frame you have data, repartition it to 4. Now these workers, these executors will take that, to shuffle the data across the machines to make it into 4 partitions. or if I want to say filter, so that
Right,
filter
let's say
is
we're-
sent to the each executor. So each executor will filter, apply that filter for the data they hold on that machine.
Oh, so this Spark context will directly talk to the worker nodes.
Yes.
That's what you're saying.
Yeah.
That's very interesting. Because I mean, I have very limited knowledge, but that's a very interesting concept, because now you have to consider the facts that, okay, what if worker node 2 goes offline, things like that. Otherwise, it may run out of. So another question is, so the data though, let's say, like you mentioned, right, 100 GB file.
Mhm.
Yeah. Now I'm thinking worker node are individual physical machines, correct? Right,
Mhm.
the actual physical machines with their own CPU, hard disk, and everything. So the question is, let's say you have a 100 GB file in a S3 or somewhere on a network. Then who takes care of taking the data, that 100 GB, dividing into worker nodes, putting like a 20 GB on worker node 1 and another 80 GB on a worker node 2. Who does that? Is that a Spark context that instructs
but
worker
Spark.
nodes to do that?
Yeah, it's the algorithm with the Spark. Within the Spark context, when you do Spark dot read, that's when
Yeah,
it
we're
does
doing
all,
that, of
applies
course.
that algorithm to distribute it. So by default, it will take 200 partitions. So whatever data that is coming in, it will divide into 200 partitions and then split it onto the worker nodes arbitrarily. It doesn't have a
Yeah,
rule or something like that.
right.
Yeah.
So
So
the
we will see how
Spark
those partitions.
Okay. Yeah, I think too many questions. So that's cool. Yeah, but I never expected a Spark. I thought everything goes through the cluster manager. I thought so.
Yeah, cluster
Okay, but
manager
that's
is more
very
of a
interesting.
communication basically. But the processing is taken care by the driver Spark context.
Interesting.
Okay. Yeah. So let me okay. Let's go on to the next step to see how this partitioning and all happens. Okay. So cache here. Before getting it, just give me 1 minute. I will be back. Let me get some water. 1 minute. Okay. So we'll look at the cache today, and we'll also look at what are the partitions and other stuff that we do here. Okay. Now I'm taking the file store tables, Amazon, reading all the CSV files here, spark.read. Okay. Do we have?
When we said Spark.read, right? So is the worker node that is reading the file, or is it our program that's reading the file?
It's the driver program which passes on, it scans the file and passes on the information to the workers. It's the workers that go and read that part of the data from the file. It's a parallel read, basically.
Okay. So it's the worker node that actually take the data into their memories.
Yes.
Right?
Because see, even when you are writing, right, each worker node will write to the target. It's not like again, you are getting all the data at one place and asking the driver to write it. It's basically, so then that's where memory overflow happens. If each machine is only 20 GB and you're getting 100 GB onto the driver, it will overflow of the memory, then it will fail. So that's why whenever you do collect is the function that gets all the data from the workers onto the driver. So you should not use the collect unless you are sure that the data will fit onto the driver machine or the master where the driver is running. Otherwise, the parallelism is defined by number of workers it can read, right? So number of workers, executors, and basically the tasks, number of cores that can read parallelly from the source. Now each core or each task has a specific set of data that reads so that they don't duplicate. All that algorithm is taken care of, what data we are reading. Okay. All right. So let's run this. So it's scanning all the files, okay, and then giving us the data frame here as a DF. What I will do, I will just say display DF dot okay. You see here, this data frame is now split into 8 partitions. So actual partitions is, at the lower level. We talked about RDD, is resilient distributed data set, which is the lowest level of abstraction, right? Remember, on top of which the wrapper, the data frame is RDD plus schema and all that. If you want to get to that low level we talked about, we can use RDD. Then we talked about what are the cases that we want to. So this is one of the use case that if I want to know how many partitions that the current data frame has, so I have to get from the underlying RDD object. This is implemented at the RDD level. So data frame dot RDD will get you an RDD object, plus and in that you get num partitions. So this is now doing 8 partitions. Okay. So
this is a very interesting fact. So we did not specify the number of partitions at all. So Spark Context automatically computed the optimized partitions depending on the resources it has at hand, correct?
Yes, exactly.
All right, great. Now, so let's say, so now we are interrogating Spark Context to give us more information, right, about what it knows. So is it possible for us to, in the similar fashion, ask Spark Context to give us the number of nodes it has and the number of worker nodes it has in hand?
So now, I didn't get your question. Okay.
Like if you go back to the code. Right.
Yeah.
Let's go to the place where it said, okay, I got it. Okay. If you go up one, where you ask for number of partitions. Okay, cool. Right. So what I'm thinking is, at this point, we're asking df.rdd, right? So when we said get number of partitions, it gave 8. It could have given 20, 25, 30. We don't know, right?
Yeah.
Right? But like, do we, so I'm thinking, okay, the Spark context made the decision to divide or provide like 8 number of partitions. By looking at it, resources,
Yes.
resources meaning, okay, how many worker nodes I have, and each of the worker nodes, which is nothing but another virtual machine, how
Yeah.
much memory it has, how much disk space it has, how much CPU power it has. It did all its computation internally.
Yes.
Then somehow it determined, okay, you know what, it's best to make it like 8. So that's a very useful information, right? So what I'm trying to say at this point is, can we also know the number of worker nodes it has in hand and what is its resources are, right? By interrogating either data frame or interrogating the Spark context. Is it possible?
No, that is at the higher level, because that you get, we were looking at DAG, right?
Mhm.
Remember the DAG?
Mhm.
That's where you get how many, if you click on that stages, there it will show you, there is a tab on resources. There it shows what cluster it has used and what are the resources available for that. That's at that monitoring level that you can see what are the resources.
I see. So again, in this code, right, then can you, previously you're showing some DAG right here itself, right, in this node. Can you show that one more time? I missed that.
We have to run that job again. 1 second.
Okay.
Let me go back. Let me see if it is still active. It has some time limit. After that, it kind of becomes inactive. Yeah, it's still active because our cluster is still on. Okay, so here, if you see the environment here. You get all the Spark thing. So you get all the, see here, executor ID, executor memory. What is the memory that is available for the executor? So there are a lot of information here that it gives you, but at a high level, so you can see executors. And see here. So there is one driver, that is this memory of 3.9 GB, 4 GB. How many cores it has? See, it is 8 cores. That is why it is creating the 8 partitions.
I see. So in this case, we only have one worker node. And that's also
there's only one master, right? It's not a cluster. We single node cluster that we create.
It's a single. So it's both the master and the worker node.
Yeah.
And also
That
the
8 partitions is not completely arbitrary. It looked at resources, how many cores I have available. So I have 8 cores. So I can parallelly work on 8 partitions. That's why it created 8 partitions. Now, if the data is huge,
right,
it can
let's say
16
so let's say
partitions.
it has one more machine with another 8 cores, and then it might have made the number of partitions as 16.
16, yes.
Right?
Yeah, it looks at data and then it looks at cores. Normally, it's like 200 default. Basically, if you have the enough cores, it will create this default partition configuration is 200. So 200 partitions. Whenever you do a join or reshuffle, it creates 200 partitions. So that's the default. Then you can do a coalesce, reduce number of partitions, or you can do a repartition to a higher number. But yeah, so this is where it has derived 8 because we have only 8 cores. So it created 8 partitions. Then it will tell you how many tasks it has created to execute all of this. It has created 321 tasks. So basically 8 tasks run in parallel, so one after the other. You can also see shuffle read, how much data that it has shuffled, 3.2 KB data. It has shuffle read and write. So here also you get all those statistics. Eight cores. Yeah.
Yeah, that was my question actually.
Yeah.
So I thought maybe we thought sorry, I thought we could get this information during the compile time, not after the runtime. But looks like after the runtime is what we get this information.
Yes. Yeah, only when it runs, it creates the tasks and goes through. Sometimes it will define at the runtime, it decides to skip some tasks, reuse some of them, create new threads, create new tasks, right? So it's all runtime decisions that it takes to
Plus
maximize.
also like you could have multiple number of clients trying to run on the same cluster, right? In that case also it has to know how busy is this cluster. Let's say even we might have 8 cores, but
Sure.
maybe you have written a program and I have written a program and Anush could have written another program.
Yes.
And 3 of us are trying to run the same 3 different programs on the same 8 cores. In that case, it might say, okay, I'm going to go to only use like 2 partitions, right? Depending on how busy those are. Is that the typical case or no?
Yeah, it is, right? So it's basically the executor. If 3 jobs are running on the same machine, using the same cluster, so it has to have copy of 3 partitions. Okay, because it cannot reuse the same partition. The data sets might be different. You are using the cluster, but the file or data you are using is not the same thing, right? You are running a different job on the same cluster. I am using a different job on the same cluster. So it will have my 8 partition, your 8 partition, and Raju's 8 partitions. So it's like 32 partitions it has to hold if all 3 jobs are running. Now, it can only process 8 tasks in parallel. So it might decide I will run, Arun's 8 tasks. So yours and Raju's are still in queue. When my tasks are done, then it will pick up the next round of 8 tasks. So that 8 tasks may be Raju's tasks or your tasks on the cluster. So that's why if you see your job is not running or on hold, the tasks are still on hold, it means that the resources are busy doing something else.
Okay, so are you saying that only one task will be handled at one point, the rest are in the queue, goes in that round robin fashion?
Yeah, 8 cores, right? 8 tasks at one time it can run. It can parallelly work on 8 partitions at one time.
But not
Cluster
necessarily
is
the
only
same.
one, right? The cluster is only one.
Right,
So it can only run 8 partitions. So 8 cores, 8 partitions it can run. That's it.
Right, but not necessarily. No, my question is, can it run like your program and my program at the same time?
No, because there's only one core, right? It is already working on this. Whether it is my 32 tasks that are pending or my 16 tasks and your 16 tasks that are pending. The cluster is the same. For it has a job to run and it has the resources to run. It can run 8. Whatever tasks that are coming, it will queue up, run it. When it is done, it will pick up the next ones.
Okay.
Thanks. Adding to so for example, in your cluster, right? You have 8 core machines, right? You have 4 of them. You have 32. Right? So now for your job, you think
Your voice is not clear, Anush. I don't know.
Is it clear now? Is it better now?
Yeah. Yes.
So now, your job is split between those 4 nodes on the cluster, right? But within each node, there might be memory or there might be any task which is freedom, correct? So is it not possible? Is it that until the whole job is done, it's not going to even go to the next job and allocate it to the P node, or so for is it like job wise split among 4 nodes, right? Irrespective of all 4 nodes working parallelly on it to complete the job, right? So until then, none of the 4 nodes will be even willing to pick up the next job. Is it
No,
that way?
yeah, no, it's not like that.
Okay, so that's where
Each node gets their round robin priority. Okay, whichever gets first into that node yeah, I understand. So your 4 tasks might be completed from one node, but the other node might be working on the task from other job.
that's possible.
Yeah, you have to wait for that. So that's why, shared clusters have to wait. But obviously, like when you submit the job, all your tasks get the same priority and all the nodes, right? Then the next job is submitted, they get the next priority. It's not like half of the tasks get higher priority and half of the tasks get lower priority. When you submit the job, all the tasks of your job get the same priority across all the nodes.
Correct. And if one node finishes that task, it can pull in the next.
Yeah, it can see if one node finish those tasks, it can pick up the next task in queue for that node. It doesn't have to be for the same job.
Correct. So when it's freed up, it can pick up anything.
Yes.
So it does not.
Yeah. Okay. Yeah, so that's kind of very advanced topic. And so as we are moving, so this is all just to understand at a high level, because as we are moving forward more and more, as I said, right, you are not, first thing is you don't not worry about the size of the cluster. Now that we have auto scaling, it will automatically add and remove the clusters based on the volume and the complexity. The second level is even that cluster is also going away. There's the concept of the clusters is also going away as we move towards serverless. So all that is now abstract from the users. You don't see, or you don't need to see which cluster, how many machines, what size and all. Everything is hidden. You just say serverless compute. Databricks will automatically define and decide how many machines it has to use, what memory it has to use based on, again, your data set and the complexity. So all of this is kind of being simplified for you. So you don't have to, unless even if you're using serverless and you are not getting the results, or it's getting stuck, I don't see that happening. Memory errors or taking long time or whatever. The argument is that it doesn't matter in terms of cost if you use a smaller machine for a longer time or a bigger machine for a smaller time. You're going to end up with the same cost. So why not use more power and finish the job in less time? Unless you want to say, no, I don't want, still want a smaller machine and I'm okay with running for longer times. But Databricks says you will have cost efficiency if you just go and use Photon and then use the serverless to finish the job in a smaller time frame and let them handle everything. But that's where we are going as an industry, right? So they want you not to worry about resources. As a data engineer, you should not worry about all these executor, memory, thread. This is all low level details, right? Where hardware level details and performance level details, where this processing power and all of that, it's a different field. It's not something that the data engineer should worry about. The data engineer should worry about what is the best way to handle the data sets, what transformations, how to reduce the shuffles. So you should focus on that and writing the code to perform easily on the calculations and improve the efficiency of the program itself. So that's where your focus should be, to design the best possible job or transformations or ML programs. That's where you should focus on. And let the performance and running the job, leave it to the platform. Okay. All right. Now, yeah, so as the systems are getting more and more intelligence being built into the machines, into the platforms. So these problems, more and more move towards the auto handling. And we get to focus on solving business problems, how to solve a business problem kind of thing. Okay, so let's go back to what we were talking about, caching. Okay. So we run this and then we see, okay, it has 8 cores, and then we are doing 8 partitions here. I'm doing a df1, which is select from the data frame, df, right? So this is the df. And I'm doing whatever transformations in this to do everything. And then I'm storing in df1. Okay. So I will run this. Now you can see there is no processing happening yet, right? There are no actions. This is a transformation. This is just scanning, and this is just the transformation. Have you seen any processing yet? Lazy evaluation, right? Guys?
Yes.
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 Okay. So next is I'm creating another data frame df2, which is I'm deriving from this df1. Again, filter. Filter is a transformation, right? So again, there is no execution here. Now I'm creating another data frame df3, which is dependent on df2 with column category, df2.main category and subcategory. I'm doing some transformation, adding a new column from df2 and then calling it df3. df3, right? Again, transformations, no processing. Creating another data frame df4 dependent on df2. More discount. I'm saying discount price, reducing the discount price and creating another data frame. Still no processing, transformation. df5, again, df2 dot with column name image. I'm just combining both name and link here. So that's it. Again, there is no transformation. Now, if I look at this df5, df4, and df3, all of these are derived from data frame 2, right? And data frame 2 is derived from data frame 1. Data frame 1 is derived from df, from Spark Read. So basically, until df2, I am following the same process. And 3, 4, 5, I am using different transformations on df2, correct?
Yes.
Okay. Now, I want to calculate df3. So if I want to calculate 3, I just call an action called display on data frame 3. So when I calculate df3, what it does, it goes and calculates df2 because it needs df2 here, right? And it goes to df2. df2 needs dependent on df1. So it needs to first calculate df1. So it goes here and then it says, say for df1, I need to calculate data frame df. Then it goes here and then it says, hey, df is this. Now go execute this. So first it gets execute df, then it executes dot select and gets df1, then it executes dot filter, then gets df2, then it executes with column category and gets df3, and then it displays the count. So that is how the lazy evaluation goes back. See, now it is triggering the jobs to do all of that transformations, calculate all the data frames that it needs to get to DF3. Okay. Now check how much time it has taken, 15 seconds. Okay. To do all of this transformations. Now I'm going DF4. So what does DF4? Same story. It has to get DF2, it has to get DF1, it has to get DF, it has to do Spark read. And on DF2, there is a different transformation to get data frame 4. Now I'll go DF4 at count. See again, Spark jobs, calculations, DF2, DF1, DF, Spark read, everything. 12 seconds. Okay. Now calculating DF5. Again, Spark jobs, again, processing, all that stuff. Okay, 12 seconds. So it's basically 12 seconds, and 15 seconds, correct?
Yes.
Look at the DAG. So all of this and this. Shuffle. All black dots, okay? Look at this DAG. Same thing, all black dots at each point where it is reading and processing. Look at data frame 3, all same black dots at each node data points where it is accessing the data. Now what I will do, since I'm seeing here, this part from here till here is same. Everything is dependent on DF2. So I want to go and say, hey, every time, why are you doing the same thing over and over again? Why don't you cache the data frame 2? Okay, I'm going to cache this part so that all of these, you don't need to do everything. You do this once and next time reuse that if you have a cache. So for that, what I will do, I'm going to do df2.cache. And then this is also a transformation. I need a action to execute this. So when I execute this, it will go back, again process df2, but this time it will cache. Okay. So again, it is processing df2, might take like 15 seconds like last time. 15 seconds. So it's calculated data frame 2. Now I want to go and do the data frame 4, 3, 4, 5, whatever I want to do. Okay, let's say 3, data frame 3. I will run this. See how much time it has taken?
1 second.
Less than 1 second. The same display df3.count. We go up and do same here, display df3.count, 15 seconds. Now it is less than 1 second. Because it is using the cache. Now if you go and look at the DAG, now you see a green dot here. Last time it was all black, right? Now you see a green dot. It says this is a cached data set. It is using the cache and not calculating the entire data sets again. So from here, it will picking up the cache. So that's what in the DAG, the green dot means. So wherever there is a green dot, it means there is a cached data set that is doing in-memory table scan. It's not doing the entire table scan. It's doing from in-memory. That is caching. Cool. So you can do all data frame 4, less than 1 second, data frame 5, less than 1 second. Everywhere you go, you check, you still see the green dots where it's reading from the same data frame. Cached data frame. Okay. This is from cache data frame. Now I can go and say, I'm removing the cache unpersist. I do the unpersist. And then now I want to go and do the same thing, df3.count. Again, the same thing starts. It will go and again, now df2 is not there. I have removed it from memory, the cache. We'll go back and again start calculating everything. So same story, 11 seconds, 11 seconds, 12 seconds, whatever it is. Got it? So this is how you have to see if you are saying that this based on your transformations, you are reusing the same data frame again and again for different transformations. You can choose to do a caching of that data set. Now, when I do cache, there are a couple of options, not couple of options, some options how you want to do the caching. So first is what are the different types that you can do caching is, let's go here. So these are all the cache options that are available. Memory only, which means all your data frame is cached in memory, RAM of the cluster. Memory only serialized. It is memory only, but the data is serialized. Now, when you do a serialization, whenever you have to retrieve it back, it has to do deserialization as well. But it will kind of reduce the amount of size of the data set that you're storing in memory. The size will reduce. You can store more data in the memory. Even if the data is bigger, you can still fit it into the memory. But then on the other hand, the trade-off is there is some IO that happens in doing serialization and deserialization when you access that. Second option is memory and disk. Say, for example, my data set is 10 GB and the data frame 2 that we are caching is 10 GB, but I only have a memory of 8 GB on the memory. So if I use this option, up to 8 GB of the data is stored in the memory and 2 GB of the data is spilled onto the disk. So when you access DF2, the first 8 GB of the data of the data frame 2 will be read from memory, and the remaining 2 GB of data is read from the disk. So there is again some network IO that you're reading from the disk. But still it's a trade-off. Like you don't have the entire memory available to store your data set. So whatever is available, you are putting in the memory, and the rest you are putting on the disk. And then from the disk, you read and write. So memory and disk with serialization. Again, same thing. So in memory, let's say, for example, the same example, your data frame 2 is 10 GB. Your memory is 8 GB. I cannot fit 8 GB, but if I do serialization, maybe it comes down to 8 GB. So I will put it in the memory. 8 GB, it fits. But if I don't do serialization, then it spills into disk. Okay. And so that's how it happens. If I don't do serialization, it will spill into memory and disk. If I do serialization, maybe it fits into the memory. So it goes everything into memory only. I can use that. Even after that, if it doesn't fit, then you do serialization. And then you do, even after serialization, let's say it's 9 GB. So 8 GB goes here and 1 GB goes to the disk. And then you again go to the serialization. So that's how these options work. And then you have to decide which one works best based on your volume of data and, how you memory or the cluster memory that is available or worker memory on each machine that is available. Disk only is simple. You are just taking the entire DF2 and storing it on a disk so that every time you go to the disk and read it, not in memory. So where in the disk, you will have a lot of space available, but then IO will be there when you are reading and writing back to the disk. So these are the different options that available when you do cache and persist. So persist is basically cache only, but it is memory cache with memory only option. Okay. So when you are doing a cache, Yeah, df2 dot cache is same as memory, persist with memory. But if you want persist, you can use any of these options. Okay, so both are same. This is what it explains. If it does not fit into the memory and you still use memory option, it gives you error, memory error. Any questions on the caching?
So when we say caching and all, does it use Redis and in-memory databases like that, or it's all?
No, it's just your worker machines in memory. That's it. RAM, whatever your cluster you have, just writes the data into the memory as a file. That's it.
Oh, okay. So no other databases are used, right? Like
No,
for example,
no
we know that
databases.
Kafka uses RocksDB, and even Flink uses RocksDB. It's not that.
No databases. No database. See, it's all like cluster, right? You launch the cluster and it runs on the cluster.
Not even SQLite. It doesn't even do that. Nothing. So it directly does the file IO. Huh?
Yeah, it's a raw data that just writes, keeps it in the memory.
Just
And then,
straight file IO.
Yeah.
Not no Cassandra, no Oracle. Of course,
No,
Oracle
so
is
it's all like you bring up the cluster, you run the job, and you destroy the cluster. That's it. And then if you add all of these components on top of that, it becomes heavy. This cluster starting itself will take so much of time. Installing all these components and then adding all of that.
Okay.
If you choose to, you can actually again connect to and persist and read and write from there.
No. We don't want to do that. No,
Yeah. No, by default.
Without us do anything, what is that Databricks is doing behind the scenes? I wanted to see if it's using in a certain database behind the scenes to build a.
No, it's just the RAM, in-memory RAM that it writes the files.
And for the disk also, disk
Yeah,
IO also.
yeah, disk or RAM. That's the files. Okay, any other questions before we move on to the next? I think we covered a lot of ground today about DAG, about distributed computing, resources, clusters, and caching. Right?
One question.
Mm-hmm.
Here, now we're doing transformations by creating multiple.
Voice again.
Oh, okay. Now is it clear?
Yeah.
Yeah. So now we were doing transformations by creating multiple data frames, right? And then we were we are caching DF2 because that is where it was going to every time to do what we're actually doing. Right?
Yeah.
So now if we are using the same data frame without creating multiple data frames, how does it change now? Can we see that? So if I'm doing all the transformations on DF, I'm not creating multiple. I'm just adding new columns to that and doing all those transformations only to DF.
No, it doesn't matter, right? See, different data frame is just a variable that you are assigning. Okay. By default, all data frames, RDDs are immutable. Even if you assign it to a DF3, DF4, or you don't assign it, you just keep calling it DF2, doesn't matter. It always returns you a new data frame object because it's immutable. You cannot change the existing data frame when you do a transformation. Whatever transformation you do, the existing data frame still remains. It gives you a new data frame with the transformation applied on that old one. Okay. Now, use the same variable, it gets overwritten so that the old data frame is just removed and you are pointing the variable to the new data frame by reference. It's a pointer. Now, if you are pointing, saying you are calling it DF3, then both the data sets are available. DF2 is still pointing to the older data set. DF3 is pointing to the transformed data set with whatever transformations you have applied. Right?
Yeah.
Okay, that's great. All right. So that covers this. Let's talk about the join strategies before we wrap up for today. Okay. So you see here, we have been doing some joins of two tables, right? Where is that? In the employee DAG, I think we did. We joined employee and department tables, right? And we also looked at DAG, what it does when I do a join. So it was showing, right, the join. I don't know where it was showing. Let's go to SQL. It gives everything. See here. So it does a broadcast hash join between these two tables, between the department and employee tables. So what does broadcast hash join mean? So basically, when you join two tables, there are different strategies that are applied. So first thing is types of joins. So don't confuse with the types of join with the join strategy. So types of joins is basically your SQL joins: inner join, outer join, left join, right join, or cross join, self join, whatever it is. These are types of joins, SQL types. I mean, you do wherever you do these kind of joins in the SQL when you're joining two data sets based on how you want to join, what kind of data that you're trying to look at. So those are types of join. All those joins are available. You can do all those joins when you're joining these two: inner join, outer join, left, right, cross, everything. Now, join strategy is exactly how is Spark handling those joins? Basically, how is it getting those two data sets to combine internally? So that is the strategy. When it does that, it has three strategies that it applies. Okay. What are these three strategies? The first one is broadcast hash join. The other one is shuffle hash join. And the third one is shuffle sort merge join. These are the three strategies that it applies. Okay. So what are these three? We will go through it. You should just understand the concept. Again, you need to understand and talk about the joins whenever we talks about adaptive query execution, which is Spark's engine that runs your SQLs. All what you are seeing, the physical plan, the actual plan, all of that is done by adaptive query execution engine, AQE. You should talk about this adaptive query execution engine. So what it does is, even at the runtime, it will calculate what strategy that it has to use for doing joins. If it is simple SQL, from select from table, this column, that column, where clause, group by, it's normal. There's nothing to do with it. But when there are joins, it will automatically kind of check what kind of joins that it has to use, strategy that it has to use to join these two data sets. Adaptive query execution, AQE engine. So in that, so standard way of the strategy is shuffle, sort, merge, join. Okay. So we will come here. And then there is a shuffle hash join, another option. So this is, I think, the least preferred of three. And then there is a broadcast hash join. So what broadcast hash join does is, when you're joining two data sets, it looks at the size of the data set. And if one table is small and one table is big, and the small table can fit into the entire table can fit into the memory of worker nodes, instead of splitting the data, it will just kind of ship the entire table to each of the worker. I think we should come back here later once we go through this. Yeah, let us first go through here and see how the data looks like in right. So for example, we're talking about employee and department. So I'm just giving an illustration, and then say I have different nodes, node 2 and node 3. Okay, node 1, node 3, node 4, 3 nodes. On node 1, I have 4 employees. On node 2, I have 4 employees. On node 3, I have 4 employees. For this is the employee data with department ID. Then there is another data set. I have also read department. So on node 1, I have 3 departments, 4, 5, 6. And then there is on node 2, I have 3, 7, 9, 12. And then on node 3, I have 3, 8, 13. So I'm joining these 2 data sets. So when I'm joining, employee 1 is on node 1. It has to join with the department. Where is 1? Okay, 1 it is not there. 2 is not there. Now let's say I have 3. So employee number 3 is on node 1 here. Employee number 3 is on node 3 here. So if I have to join these two, I have to join across the nodes. This data and that data, pull those 2 data together and send it. Now this I have to keep doing for all of the records. I have to go and search this key, take this key, and I have to go to each node and see, hey, do you have this key for department? Hey, do you have this key to department? No. Okay, next worker. Oh, I have it. So give me. Okay, I'll take this, join it here. Then next record. How much work it has to do to check across all the nodes for each key to join, right? Correct?
Yes.
Right? Are you getting this concept? Hitesh? Naina?
Yes, sir.
Okay.
Yes, sir.
Now, let's think we talked about shuffling, right? We said we want to co-locate the data. So all data with similar keys, we move to one machine. In that scenario, 3 is on node 1 here. After shuffling, I move this record with the key 3 from node 3 to node 1 here. I am not doing manually. So when I say I move it, we don't do anything at all. This is all Spark does internally. We will just say join, that's all. Everything else Spark will take care of. So what it does is it moves 3 onto the node 1 first. Then 4. It will move 4 onto this node. So similar keys it will take. Hey, all machines having this code, send it to this node. Arbitrarily, it will choose one node and move those keys into one node. So 3, 4 from departments are moved to node 1. Then node 2, it has 5, 6, 7, 8. So it will go, hey, all departments having this 5, 6, 7, 8, whatever data, move it to node 2. So 5 and 6 gets moved from node 1 to node 2, 5, 6 here, right? And 8 from node 2 gets moved to, from node 3 to node 2. 7 and 9 are already on node 2, so we'll leave it 7 and 9 here. Then again, 12, 13, 14, 11, 12, 13, 14, wherever they are, move it to node 3. So we'll see, hey, node 13 is already there in here, so we don't need to worry about it. 12 is on node 2, so we move 12 to node 3. So now, within the node 1, it can join. So you will get these 2 records. Within the node 2, you can join. You will get these 4 records. Within the node 3, it can join 12 and 13. So it gets simplified so that we get the join simpler. So this is the shuffling that happens when you do a join. Clear? So the more
Okay.
complicated the data is, the more diverse the keys are, the more complex the shuffling is. That's where the lot of network IO, CPU, and time goes in the shuffling part. Now, when it's joining, it uses these kind of strategies to do the the join strategies shuffling thing. Now we have here the okay. So I'm taking my old data set movies, okay, and reading the movies data set and then ratings. We have already done this simple join things when we are doing batch processing. We did this. We are redoing this, but this time we are putting on the lens of, we are focusing on the strategies. What happens with the strategy when we run these data sets. So I do the ratings, okay, and then I do all right. So now we are putting on the lens to do what is the join strategy that it uses when we join the data set. So let's run this attachment. Run this. It's displayed movies data frame, ratings, that's red. Now see here, I am joining ratings with movies. What is the type of join I'm using? Inner join. It's just the SQL type that I said, right? Inner, outer, left, right, all those things you can do. And the column on which I'm joining, movie ID. So once I join, I am asking to explain plan. I think people who have worked on SQL, they already know what is explain plan. In whenever you write a SQL, you do a explain plan to see what is the cost. Is it doing full table scan? It is using indexes or not using indexes? Joins are correct or not? So all of that you used to verify using explain plan. So same explain plan is here you can do on the data frame, and I have to do an action to execute all of this. So I go here, run the join and do explain plan. So where it says physical plan, adaptive Spark plan, what it is using, broadcast hash join. Okay. File scan, single partition, executor, broadcast, file scan CSV, all of this. Inner build drive false true. Movie ID. So broadcast hash join, it has used the strategy of broadcast hash join. What does broadcast hash join mean? It means that instead of having the partitions of both the tables, okay, moving like this, 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, everything, instead of having like this, it will just take the department table, all the records, and copy it into each node. So every node will have all the data set. It's not part of the data set. It's not partitions anymore. The complete data set gets shipped to all the nodes. Now, to do that, each node should have enough memory, or our table should be small enough to fit into each of the nodes. So I think there is a limitation of 1 GB or 2 GB, whatever it is. if one of the tables is small, less than 1 GB, it chooses broadcast hash join so that there is no data shuffle. Why would I need to shuffle if all my data is, the second table is there here? Whatever records is there, I will just join in there. Whatever records is there, I will join with the whole table, right? Do you get that concept? Yeah. So basically, if I say like, again, let me put here to people to understand. Employee ID, department ID, 1, 2, 3, 4, 5, 6, 7, 8. Department, let's say HR, engineering, finance, HR, legal, finance, engineering. Okay. So if this is how it is, and then this is the employee table. Okay. And this is say department table. Department table will have HR, finance, legal, and engineering. So isn't this the smaller table where you will have 10 or less than 10 or 15 departments in a company? Employees might be 100,000 employees, right? So this is a small table. Now, if I want to join these two tables, okay, so this can be in multiple partitions. This can be in multiple partitions. Then I have to move all of this here and there. Instead of that, I will choose this to copy onto all of the nodes. Okay, so if node 1, node 2, node 3. So let's say employee ID 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is my employee table that is split into 3 partitions across 3 nodes, 3 machines, right? Let's say 9 also here. Now my HR department table, let's say that also is split. I have HR, finance, legal, right? Now, if I want to join employee 1, HR is here, so I will join with this. Now, I want to join 2, engineering, so I have to go node 1. Let's say, where is engineering? So engineering is here. So 2, engineering, I have to join with the node 3. So I have to shuffle this engineering here, all engineering things, 1, 2, 7, 8 onto one node, and then get engineering onto that node and then join, right? So that is the standard process. Complicated, right? Now, instead of that, what I will choose to do now is I will just put like this in all the nodes. Okay, the entire table now I'll put on all the nodes. Now 1, 2, 3, HR, engineering, finance, everything is here. So each node can join the tables within itself. It doesn't need to go to another node. So there is no data shuffle. The entire data shuffle is cancelled, 0. Just by shipping the smaller data set to each of the nodes. So this is called broadcasting this table. So it's called broadcasting hash join. So hashing is basically based on the keys you hash and join that. So that's why it's called broadcast hash join. So this is the most recommended type of join strategy that it should use. Again, given if one table is smaller than 1 GB, where you are joining, the smaller data set, it fits into the memory of all the nodes. Okay. That's what it says here. On the driver, there is a smaller data frame. There are 4 worker nodes. The smaller data frame gets shipped to all the nodes. See here, smaller data frame, copy, smaller data frame, copy in memory. It should fit in the memory. Smaller data frame in memory, get shipped 4 copies. If you have 100 nodes, it ships 100 copies to each node. Sorry, 1 copy to each node, that is 100 copies. Now here, larger data frame, partition 0, 1, 2, 3, 4, it gets joined with the entire copy here. So there is no data that is shuffling across the nodes here. If you see in the image, no shuffling, parallelism is maintained. Got this? Everybody? If the data set is bigger, it does not fit into the each node, memory of each node, then what happens? There is a, based on the join key, like we have seen, the data gets shuffled across all the workers. Step 1, this is shuffling. Okay. First, you shuffle based on the keys, and then you do a hash join. Hash join is basically looking at the keys and then join. That's the shuffle hash join. The same hash join, but there is an extra step of sorting on the join key. Okay. So first you shuffle the data, then you sort it by the key. So once the sorting is done, it is easier to join. So that is the shuffle sort merge join. This is shuffle hash join. This is shuffle sort and then merge join. This is the broadcast hash join. So high level, these are the 3 strategies that Spark uses. Now, even if it starts with shuffle sort merge join, and then say during the execution, it finds because you have applied some transformations and all, the data has significantly fallen. Okay. I am doing some table filter less than 100 value or value less than 100,000. Okay. Value less than where clause you put, where department equal to HR. Now the data set falls well below 1 GB. Then it will automatically change the strategy on the go, on the run, saying that, hey, now I see that this data set has become much smaller. Instead of this sort merge join, we can use broadcast. So I will change it on the go while it is executing, because at compile time, you might put the filter, but it will not know when you execute that filter, how much data will be reduced. Only at runtime, it will know after you execute that. But as soon as it executes that, it will not just blindly follow the sort merge join. Hey, I decided I will do this. I will continue to doing this. No. Once it looks at this, then it will reevaluate the strategy. It sees, hey, is it the same thing? Does it still apply? And say, no, this data set is smaller now. We can change the strategy to broadcast. So then it uses the broadcast join. So that is all built into the adaptive query execution engine, AQE. So you can search for that. So that's how it runs. So that is the join strategies we talked about. Again, you don't have to dig deeper, go into. You can actually force the joins. If you want to, you can give hint. People, again, who are in the SQL, they may know, they can do the thing. They can give hints to override that. So I'm running this. I'm caching the movies data frame here. And then I'm creating another copy of the same data frame so that I have the same size. Both the tables are of the same size. And then I'm just doing a self join. Preferred is sort merge join. I'm doing it false. Okay. Because by default, it will take sort merge join. So I am switching that off and giving a hint to use shuffle hash join. instead of sort merge join. Let's see if that does it. It will not anyway use broadcast because now the tables, both the tables are copy of each other. So they are of the same size. There's no smaller data set to do the broadcast join. Guys, are you following or is it too complicated for you?
Harun, are the data frames cached in driver node, master node, or
No,
the driver nodes?
workers. Each worker,
Workers,
whatever
okay.
partition it has, it is cached there.
Then, I mean, it should take less time to perform the join, right? Instead of 27 seconds, because they're both in the cache and then they have all the parts of. You don't need to shuffle. Okay, you're using shuffle.
To shuffle, right? If
Okay.
So if you do the, if you look at here, see it uses shuffle hash join. Okay, exchange hash partition. So even if you do a copy of it, it does not guarantee that the same partition will be on the same node. Right?
Okay, okay.
Yeah. So the shuffle hash partition is what it is using here. And then if I set the default again back to true and then use hint as merge for the sort merge join, then it will use this sort merge join. I'm using the hints to force so that we can see whether it is using or not. Otherwise, it will automatically decide what it has to use. So most of the time it uses either sort merge join or broadcast join, one of these two. So here, if you see, it should show, where is that? Yeah, sort merge join. Okay, it's the same data set, but we are forcing it to use different strategy. Here, sort merge join, we said use. Here we said use shuffle merge join. Okay. So here it takes 27 seconds for the shuffle merge join. Here it takes only 12 seconds to do the sort merge join. Right? So this is more better performance. This strategy, sort merge join, is giving better performance because after sort, it is easier to join without sort. Okay. But if it is a smaller data set, you get much better performance because there is no shuffle. It goes in 1 second. Broadcast hash join. Clear? Any questions? I think with this, we wrap up the Spark internals. So we have covered foundation batch processing, structured streaming, distributed computing, and internals, right? So we will get started with the Delta Lake next week. So what is Delta Lake? What are the features of Delta Lake? How the transactions are tracked, what is time travel, how do we do time travel, and all of that we will start next week, and then move on to live tables, DLT tables. Okay. All right. So that's all for today. If you don't have any questions, we can wrap up. I will, as usual, publish the data in a couple of hours or by end of day today.
Thank you.
And
If you could please fill up the time.
Anush, your voice again.
I have a few questions. If you could please fill up the time.
Hello?
Can you hear me?
It's like muffled. Can't understand.
Can you hear me now?
Yeah.
I have a few questions. Arun, if you could please stay back for 5 minutes.
Yeah, sure. Please.
So yeah, if others I know it's already past.
Yeah.
11.
Guys,
Yes.
want you can drop off. Thank you. Guys, take care.
So Arun, one trying to understand this now when we create the tables, right? Now we have the silver, bronze. So for example, we are in the silver layer, right? We have already created silver. Now those are persistent. They are persistent.
The tables, you're saying, do they persist or not? Is it?
Yeah.
If you, they do persist.
Correct. So when we are, because whenever we open the catalog, we can just do a read, it's there.
Yes.
So now when we are doing joins across this, how does it, because it's already persistent data, it would have been allocated to a specific node or whichever it is, right, wherever it is living. So when we are trying to apply these joining strategies, how does that's where I'm trying to understand how it applies it or shuffles between nodes because it's persistent data, correct? So how does that happen?
See, it does not matter if it is persisted in the database
Okay.
or it is in the file, right? As soon as you read it, all the data is on
Got
your cluster,
Okay.
on your machines, nodes. So it's again distributed on the nodes. It doesn't matter you have read from CSV,
Okay.
you have read from S3, you have read from another external Oracle database, or you have read from Databricks Delta table.
Okay.
Everything is just a source. As soon as you read it, it becomes your data frame, which is distributed on the nodes. So from there on, everything is same.
Got it. Yeah, I'm trying to understand because I'm more used to SQL, right? So
Yes.
that's all in one, it's in one machine and it doesn't work this way. So that's where I'm like trying to map it.
It takes time to put on that distributed lens to understand, to visualize, everything is in parts, not on the same one block.
Makes sense. Yeah, that's where in shuffling, reshuffling, it doesn't happen for us, right? In SQL.
I know.
One machine. Okay. And yeah, that's the thing, because in my company now we are having this bottleneck of SQL, right? It's a transaction system. So that's where I was trying to lead this effort where, okay, we'll either use Azure. We are trying options, Fabric or Databricks. We're more inclined towards Fabric because it's all in Azure and you have more credits for Azure.
Yes.
So that's where I was trying to understand this architecture where I could propose, okay, how do we re-architect our system using this. So that's where I'm trying to map.
I understand.
But
The Fabric is more or less same as the
data.
Yeah, same thing.
Got it.
Same
Yeah.
almost. Yeah.
Sorry. It is now it makes sense.
Okay. All right.
Sort of map it.
Yep. Great, man. Take care then. Have a good rest of the weekend. Thank you.
Thanks.